Okay, so anything that's in the Earth's gravitational field is going to be a projectile if it's in unpowered flight, including a satellite. Once you get satellites in orbit, they're not powered anymore. Okay? Yes, they're powered to get there, but once they're in orbit, they require no power to stay there. Okay? If we just get them going fast enough, there's no air resistance to slow them down in orbit, okay? So they just keep going. Okay, now a projectile has two dimensions to its motion, a horizontal component and a vertical component. Because we're dealing with situations involving the perfect physical world, the horizontal component will be constant velocity. That is, we're not taking into account air resistance. The object would travel at a constant velocity forever. Okay? But the vertical component will be showing what kind of motion? Constant velocity or accelerated? Accelerated, because gravity is influencing it. Okay? So what happens is, if I throw something horizontally, okay, like this, it doesn't travel like that. It does this. Okay, and eventually hits the ground. Are we all right with that? Okay. Instinctively, we correct for this when we're throwing stuff. Or, you may have done this when you were a kid with the hose, right? You're trying to spray somebody with the hose, but they're just a little too far away, so you angle it upwards. Water goes a little further because every droplet of water coming out of the hose is a projectile. Okay? It's something in unpowered flight through the Earth's atmosphere. So a little more angle makes it go a little bit further. Okay? So instead of falling down here, if I angle it upwards, now it goes a little bit farther. That sort of makes sense? Okay, this is what marksmen have to take into account. Okay, and that doesn't matter whether you're shooting a bow and arrow or a rifle or a pistol, okay, any type of projectile, slingshot even. Okay, if you want to hit a target, you have to take into account the drop. Okay, the projectile, whatever it is, arrow, rock, bullet, okay, is going to drop every second it's in flight. Okay, the longer the flight, the bigger the drop. Does that sort of make sense? Okay, so when a marksman is aiming for a target, okay, if that target is a significant distance away, they don't aim for the center of the target. They aim above. Okay, that corrects for the drop. Or they adjust their scope. Okay, if it's a marksman shooting a rifle, they usually adjust their scope. How many people have seen the movie Saving Private Ryan? Okay. If you haven't, there's a scene in Saving Private Ryan where their sniper is trying to shoot another sniper who's in a clock tower. And he's 800 yards away. So he takes his rifle scope and he says, it's 2 clicks. It doesn't mean 2 kilometers. He clicks his rifle scope twice. And all that does is adjust. So this is my bad drawing. Okay. So what he does is he adjusts the scope so that the scope isn't pointing straight down the rifle barrel. It's actually pointed at the rifle barrel, which means in order to get his target in the crosshairs, he has to do what with the rifle barrel? He has to move it up. So instead of shooting this way, he's actually going to shoot this way, okay, and account for the drop that the bullet will experience over the 800 yards to target. That sort of makes sense? Okay. Longer that shot is, more the bullet will drop. Okay. So people who are making long shots, like that Canadian who has the world record for, it's kind of a morbid world record, but the longest kill shot, okay, that's 4 kilometers. Like that bullet dropped a long way. He probably didn't even have the target in his scope. He probably just had to aim at a spot. Like a bird. Yeah, like a bird way above or something like that, and just pull the trigger. Boom. Okay? All right, so that's kind of how that stuff works. Does that sort of make sense to everybody? Okay, so that's what projectiles do. Now, the simplest projectile is anything that's just dropped. Okay? If I drop something, it just accelerates down towards the ground. It has no horizontal component to it. It just falls. Okay? And it undergoes uniformly accelerated motion at 9.81 meters per second squared until it hits the ground. Okay? That's the simplest projectile. Now, in the perfect physical world, does that mean something would fall pretty fast if it was actually dropped from a significant height? No. Okay? But in the real world, there's air resistance. Agreed? Okay, so there's kind of a maximum speed that you can attain while falling. Terminal velocity, right? Your terminal velocity is the maximum speed you can attain while falling. Now that's dependent on things like how streamlined you are and stuff like that. Okay? Obviously we saw the feather, like the terminal velocity of a feather is very low because it's very air resistant, it's very lightweight, okay? Whereas a bowling ball would have a much higher terminal velocity. Okay? Something like a car okay, would have a terminal velocity more like the bowling ball. Okay? It would fall, but it's pretty air resistant, okay, and so it would kind of reach a top speed and then stop accelerating. Okay? And that top speed, terminal velocity is around 120 miles an hour. Something like that. It's still enough that you don't want to get to that speed and hit something. Right? Hitting something and stopping dead at 120 miles an hour is bad. Okay, really bad. We don't want that, obviously. Okay, but that's what can happen. So here's where, like, people take advantage of most people's lack of physical knowledge. Okay, back in the late 90s, Lexus came out with this sports sedan. It was like the fastest sports sedan being manufactured at the time. By modern standards, it's pretty puny now, but okay, it was 300 horsepower, which by modern standards is not as much, but it was pretty cool at the time. It could go really fast. Their whole advertising campaign was, this car is faster than gravity. Okay? That was their advertising campaign. What they did is they took a Lexus and hung it from a helicopter and dropped it. And they had another Lexus on the ground racing it to an impact point. Okay? They were both the same distance from that drop, from that impact point, and the race was on. Now, most people will go, holy crap, that car's really fast. It could beat the fall. We all know how fast everything falls, right? Except that if it's long enough, the car on the ground has a significant advantage over the falling car because the car on the ground can continue to do what? It can continue to accelerate. It's moving along its most streamlined and aerodynamic dimension. It's continually applying power. Okay? The falling car is just falling. And eventually it's going to hit terminal velocity and stop accelerating. 120 miles an hour. All you got to do is build a car that can go faster than 120 miles an hour, and you're going to beat it there, provided you give it enough room. So people didn't think about that. They just saw this ad. I'm going to show you the ad, and they were like horribly impressed because it looks horribly impressive. Okay, when you watch it. All right, so when you watch that ad, it looks pretty impressive, right? I mean, the car is falling. It's totally filmed separately. Okay, like they make it look like the car fell right behind the one that was on the ground. Never be able to, film something like that. Somebody could die. Okay, so they're obviously filmed separately and then just kind of CG together. Sort of CG. It was the 90s. CG was in its infancy then. Okay, but it looks really impressive until you start breaking down the way they did it. Okay, which is exactly what Mythbusters did. Because everybody sent them this video and said, you got to do this, you got to bust this. There's no way that would work. Okay, there's no way the car on the ground should beat the one that's falling. And they're right. There's no way the car on the ground should beat the one that's falling if you do it equally. Okay? You make the car on the ground start from zero and you drop a car, there's no way that car on the ground gets there first. Not a chance. Okay? But if you give it that advantage of already being moving, then there's a possibility of making it happen. All right, so I'm going to show you the Mythbusters now. There. So, obviously then, okay, that ad was kind of full of crap. Okay? Under the perfect conditions, you might have been able to replicate what happened in the ad. Okay? But there, part of the problem was that the car didn't fall perfectly flat. All the way down, it did this, so it got into an aerodynamic dimension, went a little faster, seesawed back the other way, went a little faster. Okay? So it fell faster than the one in the ad, and it didn't hit the X. Okay? Something they hadn't taken into account. I mean, to get something like that to fall perfectly straight down, no crosswind or anything like that is like basically impossible. Okay, so it hit like 50 meters away from the X, okay, which was actually good because then they didn't wreck both cars. One car was still able to keep driving. Okay, does that sort of make sense to everybody? Okay, so that's the simplest projectile. It's just something that falls. Okay. The next simplest projectile is one that's fired horizontally. Okay, so if we fire something horizontally, okay, it looks like a car driving off a cliff. Okay, so how many people have seen Thelma and Louise? Okay, don't. If you don't like Susan Sarandon, don't watch it. Anyway, at the end of the movie, it's like the best part, okay, because you've had to listen to them all through the movie. It's a terrible movie. They drive this T-bird off a cliff. Right, because the police are chasing them and they're going to go to jail. And rather than go to jail, they drive off a cliff instead. See, there's a lot of flaws in this movie. That's not a good decision. Okay, but anyway, they drive off. I was the only person in the theater who cheered. I got a lot of dirty looks in the theater. Okay, so this is what will happen to a car that drives off a cliff. Agreed? At first, it's like, oh, it's just flying. And then very quickly, gravity takes over. Okay, you've got whatever horizontal velocity you had, even if you're going really fast. And at first, it seems like that's all you have. But because that velocity can never get bigger, but the one vertically can, your motion goes from being entirely horizontal to being almost entirely vertical, okay, by the time you hit the ground. Right? So anytime you throw something off a cliff, or if you run off a diving board, okay, or something like that, that's what you see. Okay, is a motion that looks like that. Right? That motion has a horizontal part and a vertical part. So whenever we're dealing with projectile motion, we want to separate the two parts. Yeah. Okay, so vertically speaking, if something drives horizontally off a cliff, how fast is it going vertically? 0. It has no vertical motion yet. It is just driven off the cliff. Now, I don't mean it's like Wile E. Coyote, you know, who can like run off the cliff and fall until the roadrunner points out to him that he's no longer standing on anything. Okay, it's not like that, right? But initially, your vertical velocity is 0. But vertically, you are going to accelerate at 9.81 meters per second squared downwards. And you're going to fall for as high as the cliff is. That'll be your displacement. So let's say that this cliff is 90 meters tall. Okay? Anybody with me on that? All right. So let's say that the car drives off this 90-meter cliff at 20 meters per second. Okay. Now we have some information horizontally. We know that horizontally, the speed of the car is 20 meters per second, and we know that that's not going to change. There's nothing to speed up the car or slow down the car in the horizontal plane. Okay? Because now it's not on the road anymore, right? The wheels don't work when you're falling through the air. Okay. All right. I want to figure out how far from the base of the cliff the car will land. Well, we use the term land. Okay? It won't land, it'll crash. Okay? But we want to figure out how far from the base of the cliff it's going to land. So I'm looking for its its horizontal displacement. And I know that this won't change. So what formula am I going to likely use here? What formula do we use for something traveling at a constant velocity? Simplest one we talked about the first day. V equals d over t. All right, so that means I need to know how long the car is going to fall for. Can I use this information to calculate it? Yes. Okay, so most projectile motion problems involve you using either the horizontal information or the vertical information to get time. Okay, because time is actually the same for both the horizontal and the vertical parts. In the same way that for a boat question, the time to get across and the time for going downstream are also the same number. Okay, there are two components happening at the same time. All right, so I'm going to solve for time here, and I've got VI, A, and D. So that means I'm going to have to use this formula. But that's okay, because VI is 0. All right, so I'm going to solve for T, which means divide both sides by half of A, and square root. I've got my time. So I'll figure out how long the car falls for in this situation. So it's going to fall 90 meters divided by 1/2 times 9.81. That could be negative and that could be negative. Doesn't matter if you make them both negative or if you don't. Okay, so 90. Okay, this thing is going to fall for 4.3 seconds. It's a long time to fall. A lot of time in that 4.5 seconds. Okay, so this thing is falling for 4.28 seconds. Now, the entire time that it's falling, all 4.28 seconds, it's also moving at 20 meters per second horizontally. So yes, while you're accelerating downwards and you're going to reach a very high speed doing that, you're also still traveling horizontally at 20 meters per second. Okay, so if I want to calculate how far it goes, that's V times T, so 20 times 4.28. Okay. they're going to hit the ground 86 meters from the base of the cliff. A pretty long way. Right? So that's how a horizontally projected projectile would work. Okay, you have a vertical component and a horizontal component. So if you remember yesterday, I told you when we did projectile motion, it was going to use v equals d over t. It was going to use acceleration, and eventually we're going to get into some vector stuff. We'll get into vector stuff when we start looking at projectiles that are projected at an angle. Okay, questions so far? So we said earlier today, when you were a kid, you were playing with the hose. If you fired it horizontally, it would only go so far. But as soon as you angled it, it would go further. Okay? And the reason it goes further when you angle it is because you give it a vertical component that is now positive. So it's going to take gravity longer to pull it back. Everyone okay with that? It's going to start out moving upwards and then come back down to Earth. So anytime you have something like that, the projectile will follow what we call a projectile arc. Right? You see this, if you throw a ball or anything like that, it follows this arc that eventually comes back to the ground. How far it goes horizontally is dependent on two things. How fast you throw it, okay, so that would be this, the projected velocity, and the angle at which you throw it. Is there a halfway point on that? Like, is there a point where when you keep angling it that it eventually starts coming back? 45 degrees, yeah. Okay, 45 degrees is that angle where it starts to come back at you. Okay, it's going to be in the air for longer because you're putting it higher into the air, but it's not going to travel as far after 43 degrees, or sorry, 45 degrees. Okay. All right, so this is how we project something at an angle. This is what Hollywood screws up all the time on purpose to make things look cool in movies. Okay? See, Hollywood special effects are all tailored around something called suspension of disbelief. As long as they can make something look real enough to suspend your disbelief until the scene is over, you will accept it. And you'll go, wow, that looked really cool. Okay? The problem is that if you're smart enough, that suspension of disbelief is not long enough, and you're watching something and you're just angry. That's me and Mr. Big. Okay? Remember we watching movies like, are you kidding me? Who the hell thought that up? That's just dumb. Some of the stuff that goes on in Hollywood movies is just beyond dumb. Okay? Especially now. Okay? Like back in the day, suspension of disbelief was a lot different because there was no CG. If you wanted to jump a car over a river, you had to jump a car over a river. Okay? You literally had to put somebody behind the wheel and say, floor it, and hit that ramp. Okay? That's when stunts were real. Okay? Stuntmen were cool. Okay? Now it's, we'll just do it by remote control, we'll fly a drone over top, and then when it crashes, we'll just CG the rest, and it'll look like it landed, and it's all fine. Okay? And that's what we do. Okay? CG can make a lot of things look really, really cool. It should. All right, so I'm going to show you a couple of videos of that. And we're going to poke holes in movie physics like crazy here.